Such a good turnout for this evening's lecture. My name is Professor Deborah Johnston and I am the Deputy Vice-Chancellor here at London South Bank University. Now, whenever I give a public talk like this, I always have an apology that I give right at the start, which is to say I do have a stammer, I will get stuck on words and it will be completely fine. What I have to add this evening is I'm a little bit croaky. It's all very safe, it's nothing serious, and I'm sorry if I'm a bit croaky through the presentation, so a second apology. However, it is my pleasure to welcome you all to the inaugural lecture of Professor Issa FInst.R. Professor Issa FInst.R. The presentation of an inaugural lecture is a significant milestone in the academic career of a full professor. So the inaugural lecture provides an opportunity to do three things: to present someone's career so far, to introduce their expertise to a new set of colleagues, to wider audiences, and thirdly, to update people on their future plans, on those future areas for academic investigation, and for the schools that the colleagues are based in, and in this case the School of Built Environment and Architecture. The event has a significance in its own right. It is an evening to stop and to celebrate. It's an evening to strengthen relationships because colleagues and alumni come back, and it's an evening to make new links for new conversations, new people that come to the event. For the university itself, it is an important way that we contribute to the public agenda. So it's our moment to showcase the impact of our research, of our teaching, and our wider contributions. So we're really pleased to have restarted our inaugural lecture series after the COVID pandemic. We had a number of inaugurals last year, and the recordings for those inaugurals are all on our YouTube inaugural playlist. So if you didn't know that we had a YouTube inaugural playlist, please go and have a look. And we have a really fascinating set of presentations from last academic year. And of course we are here and we're meeting in person, and that feels very special and very appropriate. It's special because it allows us to have a richer understanding, a different way of listening. It gives us the chance in the after talk reception to ask questions, to debate. And importantly, being here, so meeting in this place, in this way, gives the appropriate significance for such an important milestone. Meeting in person again means that I need to give those standard, those very standard ritual introductions. So if I could please ask you to turn off your mobile phones. If I could say that we are recording the event this evening. Toilets are signposted outside of the room, and because we're not planning a fire alarm test, if you do hear the fire alarm, please make your way in an orderly fashion to the nearest exit. So that ritual start to an in-person meeting is complete. That means I can start the substance of tonight's event, and that is to introduce fully and properly Professor Issa FInst.R. this evening. And to present Issa fully and properly, that means introducing him in several different ways, because Issa is someone that has more than 20 years combined experience of research, lecturing and research management across higher education and industrial networks. So I'm intending to introduce him through a chronological history, through a review of his research, but also then his wider impacts on the academy. So that chronological journey. After coming to the UK from Syria in 1985, Issa graduated from City University's Department of Mechanical and Aeronautical Engineering in 1991 with a BEng honours in Mechanical Engineering. In 1995, Issa joined the Thermofluids Research Group at LSBU as a research assistant. And at the same time, he pursued a part-time PhD on enhanced heat transfer, completing that in the year 2000. Then after spells in Brunel and in industry, where he won the Energy Institute Innovation Award for, in 2005, and the Institute of Refrigeration Kenneth Lightfoot Medal for the academic year 2007-2008, Issa came back to LSBU as a senior lecturer in 2007. So this gives us a chronological history. What that doesn't tell you is Issa's research contribution and the impact of his work. So Issa's expertise, for the layperson, for the explanation that I needed, his expertise is in designing and developing better heating and cooling systems and technologies. And with his research spanning more than 20 years, he's made significant contributions to the advancement of engineering knowledge at national and international levels. And that includes over 120 conference and journal articles, and the development of 15 novel research areas and technological advances. Issa also has an excellent record of securing and delivering on research and enterprise funds, and in particular, championing interdisciplinary research that aligns with UK industrial strategy. So as a PI or a co-I, he's been involved in projects worth over £4.3 million since joining LSBU. This includes 4 industry match-funded PhDs and 2 EPSRC case awards, 1 TSB project that led to a knowledge transfer partnership, and many other small and medium projects. He has had 8 successful PhD completions, and he is a chartered engineer and has been active in developing skills and training programs to support industry, such as Skills for Climate Change for the Institute of Refrigeration. His contribution has been even wider than that. He has taught extensively across both built environment and engineering courses in BEA, and he's been student enterprise champion for the school for a period of four years. More widely still, he's had a significant impact on this School of Built Environment and Architecture's research profile. He's had a long involvement both with the school and the university research committee, and was fundamentally involved in developing the school submission to the recent UK Research Excellent Framework, and that submission was excellent. The submission achieved a GPA of 2.93, which was the joint highest in the university, with 77% of school research classed as being at least internationally excellent in quality. And this was from a standing start. This was the first time that submission had been made. More than that, he's been a journal editor for some time and a reviewer for numerous journals, and he has widely examined PhDs and been an external examiner. So we see a significant contribution to the sector, to the academy. More than that, in his spare time, and I think we begin to wonder what spare time it is that he has, he's been on the international board of reference for Peacemaker Trust, which is an NGO, a charity, which focuses on peacemaking and religious harmony projects. He's been on the Humanitarian Aid Steering Committee for the Syria Support Movement charity, and has also supported the work of several other charities such as Feed the Hungry, Solar Aid, and the Samara Aid Appeal. I've been told that he has several hobbies in the remaining time that exists. I believe he was a keen motorcyclist and has recently started learning to play the oud, which is an Arabic stringed instrument similar to the lute. I'm not sure if he's got any plans to serenade us this evening. I always ask people, tell me about the professor who's being celebrated this evening. And when I asked people this question about Issa, I heard superlative commendations. So one colleague said, as well as an impressive research and teaching CV, Issa is incredibly diligent and dedicated to the school and to the subject area. And as an example, this person said, he even goes into the labs to fix broken equipment, which probably isn't on the job description for the Associate Dean, Research and Enterprise. It certainly isn't. But it's just one indication of the dedication that Issa has shown to his subject area, to the academy, and to LSBU. So, with these commendations ringing in our ears, I would like to ask you to join me in welcoming Issa to deliver his inaugural address.
Just looking around the room, I'm humbled to be amongst so many colleagues, friends, guests, distinguished visitors as well. Thank you very much for attending tonight my inaugural lecture. I hope by the end of the day you will take something with you that is helpful in the future discussions, whether be it today or later. I'm also grateful for the university and all the friends and all of the colleagues and the family and the students for all their support, because without them I wouldn't have been here. Also, there is distinguished guests from the HBBA, the Hungarian British Associations, and the chairman and the chairwoman are here. Thank you also for joining us. They invited us to Hungary last couple of weeks, and we met quite a high delegations in Hungary. Thank you for joining us. What I would like to start first is repeat a little bit of what Deborah said, and about my background, and slightly elaborate a little bit about how I ended up being here in the UK at LSBU. 1985, I came here to do a course of English, 6 months. And didn't that 6 months end up being 32 years? By the time I came, it was too late to attend the college. The course had finished, and it was September, October, when they wanted me to come and join, and by that time it was too late to go back to Syria. So I ended up staying 1 more year. But the truth is, I actually didn't have the money to go back. And it was very difficult times in the 80s. Not realizing when you are a new immigrant to a new country, you think £500 will get you through quite a lot. It's actually, you realize that it pays for about 3-4 weeks of rent and subsistence. So I ended up staying, and my brother, all gratitude to my brother, he supported me. And I ended up going briefly to Hurlingham and Chelsea School when they said, oh, actually, you need to go to a fee-paying school. So you need to go to a private college. You're not allowed to go to state school. So I ended up looking for a college anywhere in the country that I can afford £10 installments. And you could tell there isn't any. So we were running around and not realizing the first offer I got was to do my O-levels was a bill of 2,200. That was the cheapest fee. So students who are at LSBU, you're getting a good deal when you are paying low fee, and actually the fee for PhDs now part-time is about £2,500–3,000. So it's good for part-time PhDs, and for full-time about 4,500–5,000. So at that time, to do some O-level, 4 or 5 O-levels, 2,200. And I was lucky to meet this man, BEng, who really saw something in me, actually, and gave me 50% scholarship. And I'm ever indebted to David, because he gave me 50% scholarship, and he said, how would you like to pay the rest of the money? And I said, can we bring it every 2 weeks, £10 or £20? And he said, okay, I'll tell you what, you work for me. You work for the college with the other 50%. So I ended up working for David at the same time as studying. So I was the postman for the college. I was the librarian. I was the maintenance man, young man at 16. I was the painter. I was the decorator. But it taught me something. And I did my O-levels, and then in the summer, I thought, I don't have to work for David, so I went and worked outside the college. When my brother came and turned up at the place where I was working, and he said, David would like to speak with you. So he said he wants to see you tomorrow, right? You need to finish and come with me tomorrow. So I went with my brother and to see David, not realizing actually it was the O-level results. I forgot completely about the O-level results. Young boys, I did my exam, forgot about them. I was working, trying to earn some money, support myself, to, in a way saying thank you to my brother, who was also helping me and supporting me. So we went with my brother to BEng, and David, so the colleges get their A-level results before us, opened up and says, young man, you've done us proud and you've done your brother proud. And I thought, oh, thank you. What is it? Is there some money? And David said, no, you've done very, very well. I'm proud. You've got, I think it was either 5 A's and a B. And he says, for that, I'd like to offer you the same scholarship next year, 50%, and also to work for the college. So eventually, I actually then did the A-levels at BEng in 1 year. At the time, A-levels were done in 2 years, but because of, I couldn't put any pressure on David, I said I'll do it in 1 year. So I ended up doing my O-level and A-level at the college, and I got a place at Imperial initially to do material engineering, but I really liked aviation. I liked the planes and to be in the space and so on. I wanted to initially do aeronautics or to become a pilot, but the closest to a pilot was an engineer, an aeronautical engineer. So I ended up joining City University at the time, and at City University, I went in to join mechanical and aeronautical engineering are taught together. So the first year was joint curriculum. But I realized that when they talked to me, they said to me, second year for aeronautical engineering is slightly more intense. You need to attend more. I said to them, okay, what's the mechanical engineers need to do? They said they get some Wednesday afternoon off. They get Friday afternoon off. So I said, that will do. Then I could go and work. Okay, so I ended up opting for the mechanical engineering degree. And it was brilliant. I don't regret it. And I managed, whether be it a mechanical engineering, electrical, building services, it is what you achieve, and I am proud of what I have achieved. And I always tell my students, be proud of what you achieve. So, but the engagement with the research came while I was working. So they did give me some hours to do work in the workshop. So I'm dyslexic as well. I have to declare this. So if anybody also hear me taking a breath, it's dyslexia as well. So if you notice any typos as well, and I am proud of being an engineer who's dyslexic, proud of things being engineered by dyslexia. So while I was working in the lab, I did notice around the back of me, there was a professor who was looking at me, and he walked out from the workshop and then returned back to the workshop, and I could see him asking the technician, is he a staff or is he a student? They said he's a student, but we've given him a few hours to do some welding. Okay, all right, he's doing very well. Then when he was in the third year presenting the project, he said, would you like to do a project with me? And I said, sorry? He said, I saw you in the workshop, and you were working with an arc welder. So for those ones who do not know what's arc welding, it's the machine that we use to weld metals, doors, metal fences. It's an electrical welding machine. And I said, what project are you offering me? What is the project that you would like me to do? And he came up with this name, electrohydrodynamics. And that was, I thought, what a brilliant name. And then he continued after it. He says, useful for space exploration. I said, okay, now my ambition, I want to go to the moon and be in the skies. That's now great. And stronger than gravity. I thought, that's great, sounds great. So, Professor, how would you do electrohydrodynamic enhancement? So Peter actually was a visiting professor at City University from Imperial College. And he said, we will use electric field to enhance the heat transfer fluids. And I thought, I didn't hear fluids. I heard almost just clicked like almost water, liquid. For me, at the time, I did not distinguish between the different fluids. There is insulating fluids, there is one that conductive, and so on. I just straight away related electric field and liquid water. What they taught us in electrical course, water and electricity do not go together. And I thought, I'll ask, sorry, how will you do that? And he turned around and he says, well, applying 30,000 volts across a fluid. And my hair stood up. And I thought, goodness, is he really? Is he really saying the truth? And I thought, okay. Well, he encouraged me, and I ended up doing the project. And excuse the next slide, because they are in black and white, because it shows you the cameras I can afford at the time, 1988, and I can afford a color camera. So I ended up working with Peter and the technician on putting this rig, a heat exchanger, very similar to this one here, but slightly bigger, and putting high voltage across this heat exchanger, an anode and a cathode, positive and negative, and I ended up just going around and flicking between positive and negative voltage, positive voltage, negative voltage, while the fluid is going through in the heat exchanger. And we found there is actually an enhancement. There was an enhancement, and I could see there was something in the region of 30% enhancement. So we also, what you see on the outside is a Faraday cage. So I was actually operating the high voltage from the outside. So just the university was abiding by its risk assessment and safety. So we did this cage and the high voltage generator, and he was so keen that this is safe, because then I realized it was okay, because actually the paint sprayers, the people who sprays cars, use the same guns and the same technology to spray the cars, anode, cathode, high voltage, so the paint can then be attracted to the car rather than being sprayed on the outside. In following that, I did some work for a few years, and then I was visiting my brother. I got married. I was married by then, and I was visiting my brother. Then suddenly there was a phone call, and my brother said, there's a professor, a doctor, Tassos Karayanis from South Bank University, London. That's how our university was called then. He'd like to speak to you. So I spoke to Tassos, Tassos Karayanis, sorry if I said Savas. Tassos, and I spoke to him, and he said, well, I'm here with Peter, and he's now come to South Bank University, and we have a project if you're interested in working on this project. I said, okay, what does it involve? They said, well, you could register for a PhD at part-time. So that straight triggered my interest. So I came and visited the university and went through the application process, and I got the job. And I got the job and joined the thermofluid research group, working as Tassos. Probably some of my colleagues here recognize his moustache, and Peter Allen, and some visitors from Japan, Akira Yabi, and myself there at the back. And what we were doing, we were replicating what I did in at City University for my undergraduate, but on a whole system, enhancing the heat transfer. So we designed this 12 kilowatt chiller, and we then put I'm going to use this. Then we put this electrode here. It goes inside, and the refrigerant on the inside. And there's the power generator, there's the ammeter, there's the high voltage rectifier. And we applied the voltage to this electrode. And as a result, this enhanced the heat transfer of the system by approximately 2 volts. So there is an increase of the heat transfer by 2 volts. And I'll show you, I have a video. I managed to dig out some old videos. And as you can see, there is the heat transfer. I don't know if it's clear. You can see some like convection happening. And as soon as you turn the high voltage on, there you go. You get instant nucleation, and the high voltage then pulls that nucleation and scours the surface, so increasing the heat transfer and the efficiency, not just of the surface, but the overall system. So overall, there was a 2-fold increase on the small segment, but overall system, there was a 20% increase between no voltage and high voltage. We published a few papers. And then ended up getting my PhD. And what I found, actually, I researched EHD when I was doing this. And I was really fascinated. Actually, it has made it to NASA. And NASA is currently using this technology there's a whole laboratory within NASA doing electrohydrodynamic enhancements. And this is for space. See, in space, there is no buoyancy. So a bubble, if you have a kettle in space, the bubbles do not detach from the element. So what happens, the element actually will burn. So they will be using electric field to get the bubbles moving. So you control the movements of the bubbles using almost like polarizations or some kind of ionizations of the surface of the bubbles. Anyway, going back, I went to Acrocool. I went to Brunel, and from Brunel, I went to Acrocool, and after the PhD. And at Acrocool, we were manufacturing. So I was recruited as the technical sales manager for Acrocool, and we were making water coolers. Well, the company was making water coolers, drinking water coolers. Drinking water coolers, these are the drinking water coolers you see in the canteens and so on. And at the time, that's their focus was on that. But they actually recruited me to do big chillers. And the company, in the 70s and the 80s, they were doing chillers, but they stopped because of the competition. So they brought me to resurrect it, and I did. And I started designing these big, massive chillers and heat pumps as well. It was the first company here in the UK designing bespoke chillers. So I was designing for Dawson's Rental, these big, massive other companies that rent chillers or cooling or heat pumps. I was designing for the bakeries, and all of these companies, I was designing chillers, having them made to our specifications in Italy, commissioning them in Italy, so flying to Italy, to Bergamo, and commissioning them there, and then bringing them back to the UK where they get installed. But also at the same time, the company had a smart project, and they were doing water coolers. And this technology is called the Peltier. So this is a Peltier. It's actually a cooling system working on electricity. You can see the ice is actually formulated, so I haven't just prepared this. There's an ice cube, okay? And it's actually, the Peltier is a technology that's being used in computer to cool the chips and the processor of computers. They use a lot of energy, but the innovation was to try and use the Peltier in small cooling systems. Desktop coolers, a bottle of wine for the people who loves a cold wine. So they were making this, and Roger, who was the director, was very, very keen on moving with this, and the discussion went on to say, why don't you do it? Because if this generates cooling on here, it will generate heating on the other side. So why don't you do the same? So you reclaim heat. Rather than doing just one side and reject the heat, you can use the heat to also heat on the other side. So this thing, you can have cooling and you can have heating on the other side. But what they made a mistake. Guess what they called it? And probably you see. Cool Babe. And I think that was a mistake, because quite a lot of the customers, they would call us and say, okay, no, actually, that's not what we were getting when we... So I think eventually the name was changed, so I'll turn it around. Okay, so moving on. I'm going to talk about energy conversion systems, and that's when I would like perhaps a little bit to talk about energy. That's because this experience at the company, as well as the experience at the university, has actually got me thinking, you know, this energy, so they're creating heat, cooling, and there's heating being redundant at the other side. Why don't we make use of that energy, that heating that's being chucked away? So if you look at a fridge in your house, on the inside you're keeping your food cold. If you put your hand on the back of the fridge, you've got heating. That heat, the fridge, all it's doing is capturing the heat from inside the fridge, pushing it up to a higher temperature and rejecting it at the outside of your fridge. So that's energy that's being chucked at the back of the fridge. And so what is energy? And that's when the person starts thinking. Energy is really the capacity to do work or produce an output. There's a big explanation. It's a quantitative property. But energy cannot be created or destroyed. You can move it from one form to another. All around us, around the world, even before humans were created, there was energy movements. The sea evaporates, sun radiation, then you get the clouds, you got the winds. All of these are energy, natural energy resources. We're capturing these energy resources currently in wind energy. we're capturing it in tidal wave. And but energy also is available in different formats. In fossil fuels, because trees and biomass and the results of photosynthesis, you get the trees and you get wood fossilizations, then you get the coal and you could burn that. Well, it is fossil fuel, it generates CO2. So that fossil fuel is actually, has been there for, it has energy inside it. But energy conversion, if we look, is a mechanism that we have all around us in all the areas, whether be it here, whether be it outside, whether be it the electric cars. I put in an electric cars in here with the way we eat food. Food, chemical, then transfers into mechanical or our movement into energy. And also you've got electricity into lighting. Now, in the old days, energy was the first initial form of energy conversion was the fire. So that's about 200,000 or hundreds of thousands of years ago, there was the first hominin. They converted fire. They used fire for their comfort. They used fire also for cooking and for safety. Then there was other technologies that have been developed by the early humans, and some of it was wind capturing. They used the sails to drive the boats, but also they were using wind capture to ventilate or drive the windmills or drive the grinders. And this water wheel is actually from Syria. It is actually a water wheel which it uses the river water movement is being captured and then uses it to float. But in modern civilizations, converting energy and steam in that case into a mechanical movement, James Watt was the first, and he worked with the Bolton Company to develop the first steam engine. So in modern civilizations, we have learned how to change energy from one form to another. Actually, our development as a 21st century people is dependent on the energy conversion mechanisms. And if you look here on this slide, you could see quite a lot of systems from electrical energy being generated using the variation in temperature of sea. So using the difference in temperature between the surface of the sea and about 500, 600 or 1,000 meters, there's a big temperature difference. So they use this to generate electricity. This is actually a power generation in the Vietnam. This is in hospitals. We keep the rooms, the clinical rooms cold and sterilized, and the equipment's there using energy in the bakeries. And then you've got the supermarket on the other side. Cooling is energy, but it's in a different form. Heating is energy. It's in the heat form, higher temperature, lower temperature. So this is the London Underground. This is Oxford Circus. So we're ventilating using those systems, and water, they're ventilating the London Underground. And here in the houses, you've got your solar generating hot water, which is driving the washing machine, hot water, the shower, and the sink. So energy is all around us, but currently we cannot capture it. We can't quantify it. We see its result, we do not see it. We see its results, we don't see the actual. We can eat an apple, and we know how many calories. We fill up the car with fuel, we know how many liters that is. But actually the energy that we're using, somehow we cannot conceptualize it as a quantity. And if you look at the supermarket, they use 40% of their energy for keeping food cold. So as a result of this modernization, we as a globe are currently emitting about 36.3 gigaton of CO2 annually into the atmosphere, just from the utilization of these consumption of primary energy. And as you can see here, we are about 600 exajoules. Now, my students might say, Issa, what's exajoules? Because you guys may have learned about kilowatt hours, but you've never heard of what's exajoules. That's the equivalent to 160,000 terawatt hours. So this is a new unit, so if you Google it, you will find what is exajoules. You could actually use these sources to track the energy over time, period times. You could see our energy, how it's gone from 1995 to 2020. You see this dip is actually due to COVID. So that's the dip that happened when we were in the COVID lockdown period. So we have a duty, first, to conserve energy, to use efficient systems, and to use renewables where possible, and also to consider the embodied carbon. And I love this GLA hierarchy, and a lot of my students, when they used to present their dissertations, they use this about energy. Be lean, be clean, be green, and then offset. This is one really important hierarchy that's being used in the built environment. A lot of students use this. We use it extensively. So that was my thinking about energy, drove me into looking a little bit deeper into energy conversion. Now, what I want to do, I want to do a quick test and ask a quick questions. This is a 2 or 3 bedroom, this is let's say a 3-bedroom house. I want to ask you, how many of you know the energy consumption of your homes? Put your hands up. The daily energy consumption. We've got 1, 2, 3, 4. Yeah? Yours, Harry? Yes. Okay. Right. How many of you know your tariff, your energy tariff currently? Yeah, so more people. They're thinking about money. Excellent. Right. Now, I want to ask more question. You knew, few people, about 4 or 5, knew their house energy consumption. The rest didn't. Majority of this room didn't put their hands up. Who drives? Okay. People who drives, keep your hands up. Okay. Who doesn't know the CC, the power of their car? The CC, the fuel consumption. So almost all of you know the power of your cars. How come you know the power of your car and you spend more time in your house? How come you know how many CC is your car, but you do not know how many kilowatt does of the, let's call it, the equivalent for your home? The reason for it is actually because when you go to the petrol station, you're paying, you know how many liters, and then you sit behind the wheel and you know how much is the car is going to take you. You actually know, and a lot of people compare your energy consumption. You say, my car does X amount of miles to the liter. But you do not know your energy efficiency of the house. And this is one thing that the persuasive communication of these days has failed, because we have not. Even in this crisis of energy, we still do not know our energy consumptions in the homes. We hear it on the television every day, fuel poverty, energy crisis, and yet we have not gone and reviewed the energy consumption. Although, as well, you may have a power meter, you may have an energy meter, a smart energy meter, and you don't look at it. So this is a smart house. Uses about 30 kilowatt hours for heating and about 10 kilowatt hours for electricity. But actually, that energy, that electricity that is here is only 37% of the primary energy that's being generated at the main power station. That's why electricity is more expensive than gas. The tariffs of electricity is higher than the tariff of gas, because they are actually charging you for the thermal losses, the transmission losses, and the distribution losses along the way. And these losses are almost 63% of the primary energy that went in at the main power station. And that was the reason people started putting CHPs in buildings, so they could have their own power generator, use the heat, and also generate the electricity. And then you also have some boiler efficiency and also net calorific value of the gas. So to supply this house with a 40 kilowatt hour of energy, we need a primary source of approximately 67 kilowatt hours. And that was probably costing you around, depending, I looked up some tariffs yesterday and I worked out how much you would pay for, with including tax, and you would pay including climate change levy and all of these. And a few years ago, you would have paid £2 for that 10 kilowatt hours. Now you're paying about £5 for it, electricity, and you're paying for it in here, for the gas, instead of £1.50, you're paying for it about £4.30. So your energy cost has gone up from about £4 or £3.50 to about £9. And this is for us who are working. The people, the elderly who are living on their own on small pensions, £9 a day is a lot of money. And that's where fuel poverty is. So in reality, that's what helped me when I went to Brunel and I was working with the retail sector. This understanding of the primary energy source, the cost of energy, helped me to quantify that energy. And in the retail sector, they consume about 9% of the UK electricity. Their cost of energies for one store, or it could be about 70, 80 to 100,000 pounds a year. And they had a lot of pressure from the environment groups to reduce their energy and their emissions, and they have many, many stores. So although sometimes we criticize supermarkets for their behaviors with the suppliers, but there is also some engineers, some technologists within the retail sector who tries to do things, and they have the power, but sometimes the marketing directors actually have got more power than the engineers who want to do something. So I was actually lucky to work with Doug Marriott, who was the engineering director of Safeways at the time. And Doug was so passionate about doing something, not just talk the talk. He actually wanted to walk the walk and do something. So he would come up with an idea and we would start working. And the first thing we did, he says, okay, we need to look at ways we could generate cooling in a different way. So gas was cheap. The emission from gas was also low, about 200 grams per kilowatt hours, while the main grid was about 460 to 500 grams per kilowatt hours. So we thought, can we use gas to supply cooling? So we looked on the market and we found the low temperature absorption cooling systems. This is the caravan fridges used on absorption, chemical reactions. So if you have ammonia and water, you put ammonia here, you put water, the water absorbs the ammonia and creates cooling. It's a chemical process. So we started testing these systems and see if they could do some cooling for the supermarkets, and if it can do some coolings when the tariffs are low. We also looked at another technology where we're using an ice maker, making ice at night when the temperature, when the electricity cost was low. If you remember in the 90s, Economy 7, there used to be a tariff called Economy 7, where the cost of electricity was very low in the nighttime. So if we make ice at nighttime, we store it in the tanks, and then we use it during the daytime. We tested this, and we found it actually performs better than water. The reason for it, when you're pumping through, so slush ice, you remember, you see the slush ice when you go and buy ice cream, and you say, can I have slush puppy? It's very similar to that, but you could pump it. And we found actually the heat exchangers were performing better because the temperature of the ice was not rising because it was only melting. So we had uniform temperature. We ended up with better performance of the cabinets. And also we were shifting the peak load from the daytime to the nighttime. So making the ice at nighttime and then using it during peak time when it's hot, when the tariff was very, very expensive, when the grid is asking everybody, can you lower your energy consumption? And it actually, we were proved right actually, because this would have been a perfect solution during heat waves. How many of you remember this picture? This is from The Guardian. This is 21st of July, 2022. A lot of cooling systems in London and in the UK failed because of the heat wave. If that was available in the supermarket, they had ice and cooling done during the nighttime, they wouldn't have this issue. Actually, in those days, we had a number of hotels take up the technology. I know one of the PhD students in here brought the same issue to me this summer because all of their air conditioning systems failed. And air conditioning systems perform better at night with low temperature. So at nighttime, you've got low temperature, so their efficiency is better. This was a heat wave as well in 2003. For this work, we won a number of awards in terms of the best paper, and we published a number of articles. Also, we did a book chapter. So that was a results. At the same time, we were still in a discussion with the retailers about their energy. They still wanted more, and there was a lot of talk at the time about CHPs. CHPs is a technology, combined heat and power. So rather than you're buying your electricity from the main grid and you're bringing in your fuel, your heating from gas, if you bring in a small power station to the local building or to the vicinity, you supply the gas, the electricity that you use from here supplies the building, and you use the heat, you recover the heat to supply the heating of the building. So you've got more use of the energy rather than what I said to you. You're not, these thermal losses and these transmission losses are overridden. So that was at the time a technology that was very popular, but the supermarkets were still trying to evaluate whether it is for them, because supermarkets have got more demand for cooling than they have demands for heating. And this is where we went in, worked with them, and we started evaluating their systems, and we proposed for them if they can use the technology that we discussed earlier, the absorption, which uses heat. So we recover the heat from here to drive the absorption, and the absorption technology generates cooling. Then they will get something called tri-generation system, combined heat, power, and refrigeration, all from one combined technology package. But with Doug and with our connections with we thought, we do not want to give you a solution until we look at what mechanisms can we conserve, because that's what we believe. Ethically, we believe our role as advisors is not just to give you a solution to use more energy or to make profit. It's actually how can you save energy as well in your stores. So we did a good assessment of their energy consumptions in the stores, and we evaluated what do they use for the bakeries, what do they use for the refrigeration systems, what do they use for the heating and ventilation systems, and so on. And then on this basis, we had a greater understanding of what their needs in terms of cooling and in terms of other electricity generation and so on. We also worked with the retailers on the element of putting, we were really trying to promote the idea of putting shelves. And this is from us and our contact with the supermarkets. The engineering director would like to put doors to save energy because they have the KPIs, they have the targets. The retail director saying, no, that's costing money. Every time if the customer passes in front of the chiller, they see the door shut, there's a barrier between the customer and the product. So they were thinking that barrier is losing money. So the engineering director wanted doors, the commercial director did not want doors, and it was the battle between the two. And if you look at this, it's actually about 40% of the losses comes from here. That's why when you walk in supermarkets, you actually feel the coals around your feet. And look, the supermarket is being cooled by the spillage, and then they have to heat it using heating. So this is some of the elements where energy is being wasted. We managed to have some success. There was some agreements that they do some of the fridges. So they did have, those days they put actually doors on those freezers. But on the other elements, these ones, they actually said, eventually, so we evaluated their systems and we proposed the tri-generation, so the micro gas turbine, the electricity, the heat being reclaimed to drive the absorption, so you've got heating here, gets converted in this system into cooling, and that cold water or other products comes in and cool these chillers, these cabinets. The rest of energy from the exhaust is reclaimed, and it's used to heat up the store, and then eventually we have the system. So we went a little bit further. So I know Abbas is here. He probably remembers this work and Yunting. So we went to design a pilot plant at Brunel University at the time, and we bought an 80 kilowatt micro gas turbine. We linked it up, planning, this is the schematic, and then went to the local authority, and we managed to get a planning permission. But it actually proved that we were educating the local authority, because they've never heard of tri-generation. And it was this process of going backwards and forwards and telling them, this is the system, this is how it works, this is how it generates electricity, then you import, export meters, there's exhaust flues. So eventually we managed to get it, and we managed to get it fitted. Actually, this is Doug. And we were a team working on the electrics and on this system. We ended up also buying small absorption chillers and cutting them in the workshop. That's me cutting these absorption chillers, and eventually we ended up making our own generator, and the system was running. We also did a model, economic and environmental evaluation model. This is like an Excel spreadsheet. It uses the data from the stores, and it uses our energy performance data from the components, from the boilers, from the tri-generation. And this was the results. The results was there was an energy saving about 90K, cost saving about 90K per year. And we had also less CO2 emissions. So there was economic and environmental benefits, and we proved that by bringing in different technologies together, you could get a solution. And that was what we were aiming for. But we didn't deliver the solution before we knew that the supermarket has done something on conservation of energy, on cutting down their energy consumption. So that's the BEng first. So the model also helped us. This model then was used for follow-up research studies. There was funding from the GLA to look how can you use this and evaluate the use of tri-generation systems in buildings. So that relates straight to the building. And by the way, stores are also built environment. So retail stores are also built environment. So, but we did this evaluation for different buildings, different technologies, and we found that by using tri-generation, you can, depending on the tariff, between the spark gap between the gas and the electricity, you could potentially make money or save energy. So this won 3 awards. including the Energy Institute, the Innovation Award, as well as the iWork and this iFoot, and the quite a lot of other papers that were published. Now, you might ask me, okay, what happened to it? Well, if we all go to the Natural History Museum, and underneath the Natural History Museum, which is, I love it actually, it's a beautiful place to go to, they use trigeneration, actually. It's underneath they replace one of the boilers and they put a CHP and an absorption chiller, and that is serving the museum, and they are in collaboration. I think it's the Natural History Museum and the Victoria and Albert Museum using this. Because what they use, they have a demand for cooling. They need to take the humidity out of the air. Otherwise, the humidity will damage the artifacts as well. So the air needs to be conditioned. Recently, I think it was in 2018, Edinburgh University, put a proposal for £9 million trigeneration system. The only problem currently is the cost of gas has gone up because of the current crisis, the war in Ukraine. And that's where it's becoming a hurdle in the movement. But as well, the grid is also being developed, becoming more and more renewable, which is really great. I hope the grid becomes 100% renewables. But at this stage, we're still using a lot of fossil fuels. We're about 40% still using fossil fuels. So that's why gas is currently not that popular. So potential for this is to use fuel cells, biogas, and hydrogen in the future. Issa is here. One of my students, he brought a project from the Health Trust, and Ihsan did an evaluation of how can he use CHP in the Health Trust where he works. That was his final year dissertations. We did the evaluation, and the project was accepted by his employers, and he delivered on it. Am I correct, Ihsan? Yes. And their savings are listed there. I don't need to read these savings, but there was a savings. And until this day, it's running, because I visited Ihsan about 5 weeks ago, and had a look at this technology. So it was absolutely brilliant to see some things that our students have studied, have looked at the feasibility, went to their work, and then that became a real-life project. I do have other projects. Some of the students who worked on the Battersea development, Battersea Power Station development, also brought some things, and we worked with them on this. So this is the proud moments. This is the things that I am proud of, is the achievements of my students. And this is something else as well I did. So we did buy a small business in West Kensington, my beautiful laundrette. So, and that actually, we went into partnership with somebody who was in that business. But my interest was on the energy. That was my interest. So I actually put a heat reclaimer, and I captured the heat from the dryers, and we used the heat to dry the shirts. It was actually better than the dryers. We also put solar heating on the roof of that time, and from March to September, the solar thermal evacuated tubes were the ones that were supplying the heating for the business. So the boilers were not coming on. There was a saving of approximately 45 to about 50% in terms of energy. But we also did some passive design. We actually put double glazing and various elements in the business. This is the work of my student, Shada, sitting there. We also looked at how can we get radiators working better, what kind of fluids can we have inside the radiators, and we looked at alternative heat transfer fluids, and we found between using the water and the other alternative heat transfer fluids, you could see the black area is the good temperature, the yellow area is the lower temperature. So you could see this area, this is where the marker, this is where the foil paper, it was here, and now we're getting more and more temperature, uniform temperature on the radiator using these fluids. So that was the work of Shada, and she finished her PhD in 2020. I also did not just work within BEA. I worked with other colleagues in different schools. I worked with Deborah Andrews in the School of Engineering. I worked with Liz Newton in School of Applied Science. And we worked at circular economy, and this is working because I brought the people I was working with at Brunel. They came and started working with me when I joined LSBU. And here, this company, the Bond Group, their business is making new chillers, but their director was thinking ethically, I can't keep on taking chillers and storing them and dumping them. So he developed a new business, remanufacturing or refurbishing old display cabinets. But he was having difficulties selling that back to the supermarkets. They were paying him to store old display cabinets. But there was always the thinking, anything new is better than old, even if you refurbish it. That's the mentality that was going around. And every 4 years, a new director comes in, and all they do an overall removal of the equipment, and they bring in new chillers. If you look at some of the supermarkets, you go to the supermarkets, suddenly some of the chillers, after a few years, it's brand new chillers. That's embodied carbon. That's a lot of energy being wasted. The performance is actually in the refrigeration system and the heat exchanger, not in the frame. Why do you have to change the frame? Why do you have to go and throw and dump a complete unit only after 2 or 3 years of its lifetime? It's almost like somebody coming along and saying, my fridge needs a little bit of charging. Okay, they will chuck it away and they'll buy a new fridge. So we worked with them on under a funded project whereby we were looking at the way we can quantify the economic and the social and the environmental benefits of reuse, remanufacture, and refurbishment of retail display cabinets. So we ended up developing what's known as the first calculator to evaluate the environmental impact of remanufactured display cabinets. Then that then fed into developing the circular economy persuasive communication PhD. So they actually funded another PhD on persuasive communication. And this is to encourage the directors who are making the decisions to evaluate, to find value in reusing this remanufactured display cabinets. And then Bahari here, I joined as a result of working with Liz and Deborah. We then started working with saving energy and looking at how can we save energy from using blinds and curtains. Because they're there, they're actually a barrier, a thermal barrier, so they could prevent the heat loss. So that was another success. Currently, I've got one PhD student. Ayman is actually doing a PhD on the hotel. I didn't stay in this room, by the way. So in the hotel, we're looking at the technology. How can you interact? How does the guest, and in the hotel sector or in the hospitality sector, the customer satisfaction is the most important for them. And what's happening is about energy. So they use a lot of energy, and you will find that they're actually, sometimes the air conditioning is on, and the windows are sometimes in some hotels is open, or the heating is on and the windows are open. So now they're putting a lot of IoT. The next aspect we're looking at is the interaction. The interaction now between the customer and the IoT, and the interaction between the actual workers, the employee, and IoT. So that's what we're doing. So I'm coming to the end of the presentation, hopefully, but I want to touch on the current and future directions. So current projects and future directions of travel. I think the current project we have is about SMA. Sorry, that was and SMA is a smart memory alloy. This is currently, we are using it as a match-funded PhD. Our sponsors are sitting there, Exogen are here, and we're looking at how can we use smart memory alloy to develop heat pumps, the future heat pumps. And if I was to say what smart memory alloy is, you'll be surprised. It's actually the stent that's the medical use for the heart. That stent is actually what we are using. It has a memory. It remembers if you stress it, it generates heat. When it goes back, it absorbs the heat, so it provides cooling. Heating, cooling, heating, cooling. And Mike over there was initially developing a generator, and they came to us to evaluate how we can use this and develop the heat exchange part where we could extract the heat from the smart memory alloys. So I think this is a promising technology where we will not be needing refrigerants, and refrigerants contributes to global warming when they leak. So this is what they're thinking about using, and we're working on it. Okay, so this is something that Mubarak has done, just a simulation. So that's generalized. You get cooling by de-stressing, you get heating by stressing. So that's the kind of element. So Mubarak is actually gone to heat up the water, but he will not catch us. I was going to do a demonstration for you with memory alloy. So the future is, I think the future is alternative cooling technologies, alternative heating technologies, and I think there will be a lot of new technologies coming to the market. We need to evaluate these. At the same time, there is also the potential to bring a number of technologies together. So we published a number of papers on this. I have another PhD on passive control using fuzzy logic, and Bukola is here, and she's working on how do we do natural ventilation in buildings in order to cool and to ventilate the building. So natural ventilation rather than mechanical ventilation. Mubarak is here. You want to help us? Do you want to do it? What do you want? Where's the... So Mubarak is going to do a demonstration while I'm doing... So Mubarak is going to do a quick demonstration while we're looking. So Mubarak, this is the smart memory alloy. And if you look at the way Mubarak is doing, so if you put heat on this, it remembers its original shape and it goes back. So that's the demonstration. So the people in the back, they haven't seen it. So thank you. Thank you, Mubarak. So the future. Alternative technologies, hydrogen potentially having a good future, but also we need a new approach to speed the transition to net zero. The direction of travel has been set. We need to be net zero by 2050. We need a greater emphasis on efficiency and energy carbon management. I'm pleased the Institute of Energy have come up with this guide about the energy and carbon management. We need to have a greater emphasis on net zero education, and Aaron is there, and he would be pleased that we have developed the first net zero courses, so if anybody wants to take a brochure. And also, I am a great believer that there is an opportunity for us to follow the Rolls-Royce model solution. Rolls-Royce do not sell engines. Rolls-Royce sells solutions, propulsion. They don't get, the engine is there. They maintain it, they look after it. What they sell you is the energy, the thrust. They charge you for what the engine gives you. It's the same model. Do you remember in the old days, they used to, you can go and rent a television? Yeah? So the television is the entertainment. The company, so that's the future generation. I think with energy, in order for us to save, this is the model, because I think the supplier of the technology would be responsible for its maintenance, be responsible for its installation, and will be charging us the products. We're not interested. We're not interested in how the technology, or we're interested in the actual output. We're an education institute. We want cooling. We want heating. Yeah, we're not going to go and maintain the product, and every time the boiler fails, we run around getting an engineer. So these are the elements, I think, the direction for travel. We need support for local renewable communities. Andy, I think you would like this. This is something Andy Ford has been preaching for, and it's about having local community schemes. Sometimes it's better for us as communities to bring in renewables, and we need to raise awareness and support for simple innovation and passive energy saving measures. So in summary, energy efficiency and at component levels is good, but a whole system approach could result in better and greater energy savings. Understanding the prime source of energy, how much you're using, how much is this actually at the source, gives a better understanding of the economic and environmental evaluations. Human behavior plays a very, very important part in the way we use and the energy bills. And so we need to tackle this by educating and doing something about how we encourage people to learn about their energy behavior. We need more education about conservation of energy, and we need future in providing solutions, not systems, and that's the Rolls-Royce system. And I'd like to pay a tribute to, first of all, my family, my mother, my father, and my late brother, and my students here. Chris Dyer lost his life in 2011 in terrorist attack in Tunisia, and recently, earlier this year, we lost another student, Rom Mahmoud, in an accident. So tribute to them and my late professor, Peter Allen. And a big, massive thank you to all the people, my wife, my sons, my friends and colleagues in here, and of course, my network, industrial partners, and the people in the bigger family of our research. Thank you very, very much, and thank you for listening to me.